Hello there and welcome. Tonight's gentle journey explores one of the most mind-bending questions in all of science. Do parallel universes really exist? Are there infinite versions of you out there making different choices, living different lives, perhaps even listening to this very same voice in worlds where the words come out slightly different, where the pauses fall in other places, where you decided to put on different pajamas or chose a different pillow? Before we drift into this cosmic mystery that has puzzled philosophers and physicists alike, I'd love to know where in the world you're listening from tonight, and what time it is in your particular slice of reality. Are you tucked into bed as the evening settles around you? Or perhaps you're in some other part of the globe where dawn is approaching, where the light is just beginning to creep through curtains. It's rather fitting, isn't it, that we're scattered across time zones, each experiencing this moment differently, because tonight we're going to explore the possibility that even this simple fact might be just the beginning of how varied reality truly is. And I do hope this isn't so captivating that it keeps you awake. Though if it does, at least you'll drift off, having pondered some of the most profound questions humans have ever asked about the nature of existence itself. Now settle in, slow your thoughts, and let your breathing find its natural rhythm, because we're about to embark on a journey that will take us from the quantum realm, where particles dance in superposition, to the cosmic scales, where entire universes might bubble into existence like foam on an infinite ocean. We'll explore ideas so strange they sound like science fiction, yet they emerge from the most rigorous mathematics and careful observations that human science has produced. We're going to discover that the question of parallel universes isn't just academic speculation, but touches on some of the deepest puzzles in physics. Why the universe seems fine-tuned for life, what happens when quantum measurements occur, and whether mathematics itself might be the fundamental substance of all reality. Tonight, we'll meet the brilliant minds who first dared to suggest that everything we see, everything we know, everything we are might be just one thread in an infinite cosmic tapestry. We'll learn about Hugh Everett III, who proposed that quantum mechanics requires infinite parallel worlds. We'll discover how cosmic inflation, the theory that explains the early universe's rapid expansion, naturally leads to the idea of countless bubble universes. We'll encounter Max Tegmark's radical suggestion that every mathematical structure exists as a physical reality, making our universe just one equation among infinitely many. But we'll also grapple with the profound challenges these ideas present. How do you test a theory about things you can never observe? What does it mean for science if our best theories predict realities forever beyond experimental verification? And perhaps most personally challenging of all, if there are infinite versions of you making every possible choice, does anything you do really matter? These aren't just technical questions for physicists. They're existential puzzles that touch the very core of how we understand ourselves and our place in existence. As we explore these ideas, we'll discover that parallel universes aren't just one concept, but an entire family of possibilities, each emerging from different branches of physics and philosophy. Some are quantum mechanical, splitting reality with every microscopic event. Others are cosmological, arising from the structure of space and time itself. Still others are purely mathematical, existing in the realm of abstract possibility made concrete. Each type has different implications, different evidence, and different levels of scientific acceptance. So prepare yourself for a journey that will stretch your imagination and challenge your assumptions about reality. We'll travel from the subatomic to the cosmic, from the concrete to the abstract, from the certain to the speculative. And through it all, we'll maintain that gentle rhythm perfect for drifting into sleep, because there's something deeply soothing about contemplating the infinite, about realizing that existence might be far grander and stranger than we ever dared imagine. whether parallel universes exist or not. The very fact that we can conceive of them, can mathematically describe them, can seriously consider their implications, reveals something remarkable about the human capacity for wonder and understanding. Now let's begin this cosmic lullaby and see where it takes us. The idea of parallel universes captures something deep in the human imagination, something that resonates in the quiet moments when we wonder about paths not taken, choices unmade, possibilities unexplored. Somewhere out there, perhaps there's a version of you who chose differently at every crucial moment, who took that job offer you declined, who moved to that distant city you only dreamed about, who said yes instead of no, who turned left instead of right on that pivotal day when everything might have changed. There's a version who didn't forget their keys this morning, who remembered to water the plants, who called that old friend, who finally learned to play the guitar that's been gathering dust in the corner. It's simultaneously thrilling and unsettling, this notion that all possibilities might be real somewhere, that every story gets told, every path gets walked, every decision branches into actual existence rather than simply fading into the realm of what if. But science isn't built on what feels intuitively appealing or emotionally satisfying, no matter how beautifully these ideas might capture our sense of infinite possibility. The question before us tonight isn't whether parallel universes make for compelling stories, rich material for novels and films and late-night conversations about the nature of existence. The question isn't whether they provide comfort to those who wonder about alternate lives or solace to those who regret roads not taken. These are deeply human responses to the concept, and they matter, but they're not scientific evidence. The real question is whether the mathematics and observations of physics actually require parallel universes to exist, whether they emerge naturally from our best understanding of reality rather than from our wishes and imaginings. This distinction is crucial because it separates legitimate scientific inquiry from wishful thinking, rigorous theory from appealing speculation. Throughout history, humans have projected their desires and fears onto the cosmos, seeing patterns that aren't there, finding meaning in coincidence, constructing elaborate explanations for phenomena they didn't understand. The geocentric model of the universe placed Earth at the center because it felt right, because it matched our sense of importance and centrality. The idea of the luminiferous ether filled space with an invisible substance because scientists couldn't imagine waves traveling through emptiness. Time and again, we've discovered that the universe operates according to principles that have nothing to do with what feels natural or comforting to human minds. So as we explore parallel universes tonight, we must constantly ask ourselves, are we following the evidence wherever it leads, even if it takes us to strange and unsettling places? Or are we being seduced by ideas that appeal to our imagination but lack genuine scientific foundation? This is the tension that runs through all cutting-edge physics, the delicate balance between bold theoretical speculation and empirical grounding, between mathematical elegance and experimental verification. The history of science is filled with ideas that seemed absurd when first proposed, but turned out to be true, and equally filled with beautiful theories that had no connection to actual reality. When Einstein proposed that space and time could bend and warp, most scientists found it preposterous. When quantum mechanics suggested that particles could be in multiple states simultaneously, even its founders found it disturbing. Yet both theories have been verified by countless experiments and now form the foundation of modern physics. Conversely, the steady-state theory of cosmology was mathematically elegant and philosophically appealing, avoiding the awkward questions raised by a universe with a beginning, but it couldn't explain the cosmic microwave background radiation and was eventually abandoned. This is the context in which we must evaluate parallel universe theories. They emerge from our most successful physical theories, from quantum mechanics and cosmology and string theory, but they make claims about realities we cannot directly observe or experiment upon. They solve genuine scientific puzzles, like the measurement problem in quantum mechanics and the fine-tuning of physical constants, but they do so by postulating the existence of infinitely many unobservable worlds. They're mathematically rigorous and logically consistent, but they push the boundaries of what we traditionally consider to be science. Consider the peculiar situation we find ourselves in. Our best theories, the ones that have been tested to extraordinary precision and have enabled all of modern technology, naturally predict the existence of things we can never see or touch or measure. It's as if our most reliable map of reality includes vast territories marked "Here be dragons" that are forever beyond exploration. This raises profound questions about the nature of scientific knowledge itself. What does it mean to know something if you can never observe it? How do we distinguish between mathematical convenience and physical truth? These questions become even more pressing when we realize that parallel universe theories aren't just abstract curiosities, but have implications for how we understand ourselves and our place in existence. If every possible version of your life is playing out somewhere, if every choice spawns new realities, if every story finds expression across infinite worlds, what does that mean for concepts like identity, responsibility, meaning, and purpose? These aren't just technical questions for specialists. They touch on some of the most fundamental human concerns about who we are and why we exist. Tonight, we'll separate the wishful thinking from the genuine scientific theories that suggest reality might be far stranger than we ever imagined. We'll examine the actual evidence, such as it is for parallel universes. We'll explore the mathematical frameworks that predict their existence and the logical problems they claim to solve. We'll consider the profound implications of taking these ideas seriously, and will honestly confront the limitations and challenges they present. By the end of our journey, you'll have the tools to think clearly about one of the most remarkable possibilities in all of science, that this reality, this life you're living, this moment you're experiencing, might be just one note in an infinite cosmic symphony. Before we can ask if parallel universes exist, we need to be clear about what we mean, because the term parallel universe has been stretched and twisted by science fiction, popular science, and casual conversation to cover everything from alternate timelines where dinosaurs never went extinct to pocket dimensions, where the laws of physics work differently to digital simulations run by advanced alien computers. Scientists actually discuss several distinct types of parallel universes, each arising from different theories, different mathematical frameworks, and different kinds of evidence or lack thereof. These aren't variations on a single theme, but fundamentally different concepts that happen to share the common thread of suggesting that our observable reality is not the only reality. The confusion begins with the very word parallel. In everyday language, we think of parallel lines as running alongside each other, never touching, forever separate, but somehow related. But in the context of parallel universes, the relationship between different realities is much more complex and varied. Some propose parallel universes are indeed separate and unreachable, like distant islands in an infinite ocean of space and time. Others are intimately connected to our own, splitting off from shared quantum events or intersecting in ways we cannot directly perceive. Still others exist in entirely different mathematical spaces, governed by different logical structures, bearing no resemblance to our familiar world of matter and energy and space-time. The first major category consists of quantum parallel worlds, where every quantum event splits reality into multiple branches. This idea emerges from the many worlds interpretation of quantum mechanics proposed by Hugh Everett III in his 1957 doctoral thesis. In this framework, the fundamental equation of quantum mechanics, the Schrödinger equation, never stops applying. When a quantum measurement occurs, the universe doesn't mysteriously collapse into a single outcome as traditional interpretations suggest. Instead, all possible outcomes happen simultaneously, but in separate branches of reality that can no longer communicate with each other. Every time a radioactive atom decides whether to decay, every time a photon chooses which slit to pass through in a double-slit experiment, every time any quantum system interacts with its environment, reality splits. The implications are staggering. If true, this means that parallel universes are being created constantly, at every moment, in numbers so vast they defy comprehension. The second major category involves cosmological multiverses, where our observable universe is just one bubble in an infinite sea of cosmic domains. These arise from theories about cosmic inflation, the rapid expansion that occurred in the earliest moments after the Big Bang. According to these models, inflation didn't happen just once in one place, but is an eternal process, constantly creating new regions of space that inflate and form their own pocket universes. Each pocket would have its own Big Bang, its own evolution, its own galaxies, and stars and planets. Some might have physical constants similar to ours, allowing for the formation of atoms and molecules, and potentially life. Others might have completely different values for fundamental forces, leading to universes where matter behaves in ways we cannot imagine, where chemistry as we know it is impossible, where the very concepts of space and time might take unfamiliar forms. The third category consists of mathematical universes, based on the radical hypothesis that mathematics is not just a tool we use to describe reality, but is itself the substance of reality. Max Tegmark's mathematical universe hypothesis suggests that every mathematical structure that can be consistently defined actually exists as a physical universe. This would mean that our reality, with its specific laws of physics and particular arrangement of matter and energy, is just one mathematical structure among infinitely many. Somewhere in this vast mathematical landscape would be universes that differ from ours by just one electron, universes that follow the rules of different geometries, universes where time has multiple dimensions or where causality works backwards, universes that correspond to every equation ever written and every equation that could ever be written. What unites all these different types of parallel universes is the radical suggestion that the reality we experience is not unique, that existence is far grander and more diverse than anything we can directly observe or imagine. But the differences between these categories are crucial for understanding what kinds of evidence we might look for and what kinds of predictions these theories make. Quantum parallel worlds, if they exist, are created by every microscopic event and remain forever connected to our reality through their shared quantum mechanical origin. Cosmological multiverses are separated by vast distances in space and time, but might leave subtle signatures in the cosmic background radiation or other observable phenomena. Mathematical universes exist in completely abstract realms, but might be connected to our world through the deep mathematical structures that govern physics. Each type also faces different challenges and criticisms. The many worlds interpretation of quantum mechanics is mathematically consistent and avoids some conceptual problems with traditional quantum theory, but it requires accepting that reality splits into countless branches. Every microsecond, most of which we can never observe or verify, cosmological multiverses emerge naturally from our best theories about the early universe, but they predict the existence of regions we can never reach or study directly. Mathematical universes provide an elegant framework for understanding why mathematics is so effective at describing the natural world, but they blur the line between abstract mathematical objects and concrete physical reality in ways that make many scientists uncomfortable. There's also the question of what it means for these parallel universes to exist. When we say our universe exists, we usually mean that it contains matter and energy arranged in space and time, that it has a history and a future, that it can be observed and measured and studied. But parallel universes, by their very nature, are beyond direct observation. We cannot visit quantum branches that split off from our timeline. We cannot travel to cosmological domains beyond our cosmic horizon. We cannot step outside mathematics to examine mathematical structures from an external perspective. So in what sense can we say these parallel realities exist if they forever remain beyond the reach of experiment and observation? This brings us to one of the deepest questions in the philosophy of science. What is the presence relationship between mathematical theories and physical reality? Our most successful scientific theories are mathematical in nature, using equations and abstract structures to make precise predictions about measurable phenomena. But when these same mathematical structures naturally predict the existence of unmeasurable phenomena, like parallel universes, how should we interpret them? Are they describing actual features of reality, or are they simply mathematical artifacts with no physical meaning? As we delve deeper into specific theories of parallel universes tonight, keep these distinctions in mind. We're not talking about one phenomenon, but about several different possibilities, each with its own logical foundation, its own evidence or lack thereof, and its own implications for how we understand the nature of existence itself. Quantum mechanics, that beautifully strange theory governing the smallest scales of reality, presents our first serious encounter with the possibility of parallel universes, and it does so in a way that emerges almost inevitably from the mathematics itself rather than being imposed from outside by wishful thinking or science fiction imagination. When quantum particles are measured, they seem to randomly choose one outcome from many possibilities, like a cosmic dice game where the results appear fundamentally unpredictable. A photon hitting a half-silvered mirror will either reflect or transmit, but before measurement, quantum theory describes it as doing both simultaneously, existing in what physicists call a superposition of states. An electron orbiting an atomic nucleus doesn't follow a definite path, but exists as a cloud of probability, present everywhere and nowhere until the moment we try to pin down its location. This situation troubled many of the founders of quantum mechanics, including Albert Einstein, who famously declared that God does not play dice with the universe. But the experimental evidence for quantum superposition is overwhelming and undeniable. In the famous double-slit experiment, individual particles behave as if they travel through both slits simultaneously when unobserved, creating an interference pattern that can only be explained if each particle somehow takes every possible path at once. Yet when we try to observe which slit the particle actually passes through, the interference pattern disappears, and the particle appears to have taken a definite path. It's as if the act of observation forces reality to choose one possibility from many, but the mechanism by which this choice occurs remained mysterious for decades. Enter Hugh Everett III, a graduate student at Princeton University, who in 1957 proposed something remarkable and unsettling in his doctoral dissertation. What if they don't choose at all? What if every possible outcome actually happens, but in separate universes that split apart at the moment of measurement? In this many worlds interpretation, reality constantly branches like an infinite tree, with each quantum event creating new parallel universes where all possibilities are realized. The photon doesn't randomly decide to reflect or transmit. It does both, but in different branches of reality that can no longer communicate with each other. The electron doesn't collapse to a single location. It ends up in every possible position across countless parallel worlds. This interpretation sounds radical, and it is, but it emerges naturally from taking the fundamental Equation of quantum mechanics. The Schrödinger equation. Seriously. This equation describes how quantum systems evolve over time, and it's remarkably successful at predicting experimental results. But traditional interpretations require that the equation suddenly stops, applying when a measurement occurs, that the smooth, deterministic evolution described by Schrödinger's mathematics gives way to a random, instantaneous collapse into a definite state. This seems arbitrary and unsatisfying, like having a beautiful piece of music that suddenly cuts off in the middle for no apparent reason. Everett's insight was to let the Schrödinger equation continue to apply always and everywhere, without exception. In this view, measurement doesn't cause reality to collapse into a single outcome, but causes it to branch into multiple realities, each containing observers who see a definite result. From the perspective of any individual observer, measurements appear random, because they can only experience one branch of the splitting reality. They have no access to the other branches where different outcomes occurred, no way to communicate with the versions of themselves that measured different results. The randomness isn't fundamental to nature, but emerges from our limited perspective as observers trapped within a single branch of an ever-expanding tree of realities. The implications are staggering and difficult to fully comprehend. If the many worlds interpretation is correct, then every quantum event, no matter how small or seemingly insignificant, creates new universes. The radioactive decay of a single atom in your body right now potentially splits reality into branches where the decay occurred at slightly different times or didn't occur at all. The quantum processes occurring in your brain, as you listen to these words, might be creating countless parallel versions of yourself, each having slightly different thoughts, making slightly different decisions, experiencing slightly different streams of consciousness. Right now, as quantum events occur throughout the observable universe, reality is splitting into an unimaginably vast number of parallel worlds, each following its own trajectory through space and time. This branching doesn't just apply to microscopic quantum events, but potentially to any situation where quantum mechanics plays a role, which might include everything from the behavior of molecules in your nervous system to the fusion reactions powering stars to the quantum fluctuations that shaped the early universe. If consciousness itself depends on quantum processes in the brain, as some theories suggest, then our thoughts and decisions might literally create new realities with every moment of awareness. Every choice you make, every path you consider, every possibility that crosses your mind might correspond to actual worlds where those alternatives play out. Yet despite its radical implications, the many worlds interpretation faces a curious problem. It makes the same experimental predictions as traditional interpretations of quantum mechanics. From the perspective of any individual observer in any single branch, measurements appear random and unpredictable, exactly as conventional quantum theory suggests. The parallel worlds, by definition, cannot be directly observed or communicated with once they split off from our branch of reality. This makes the theory scientifically peculiar because it postulates the existence of infinitely many unobservable realities to explain phenomena that can be accounted for without them. Critics argue that this violates the principle of scientific parsimony, the idea that simpler explanations are preferable to more complex ones. Why accept the existence of countless parallel universes when traditional interpretations can account for all experimental observations? Without them, supporters respond that the many worlds interpretation is actually simpler in a deep sense, because it requires no additional assumptions beyond the Schrödinger equation, no arbitrary rules about when quantum superposition ends and classical reality begins, no mysterious mechanism by which measurements cause wave function collapse. The debate touches on fundamental questions about the nature of scientific explanation and the role of unobservable entities in physical theories. Throughout the history of science, theories have postulated the existence of things that could not be directly observed. Atoms before electron microscopy, electromagnetic fields before radio waves, black holes before gravitational wave detectors. In many cases, these theoretical entities eventually became observable through advances in technology and experimental technique. But parallel worlds, if they exist, seem forever beyond the reach of direct observation by their very nature. This raises profound questions about personal identity and the meaning of individual existence. If there are countless versions of you across parallel realities, which one is the real you? Are you just one thread in an infinite tapestry of selves? Or does your subjective experience somehow distinguish your particular branch as special? When you make a decision, are you choosing your path through reality? Or are you simply becoming aware of which branch of an already determined tree you happen to inhabit? These questions extend far beyond physics into philosophy, psychology, and the deepest mysteries of consciousness itself. As we continue our gentle journey through the landscape of parallel universe theories, the many worlds interpretation serves as our first guide into truly strange territory, a place where mathematics and reality intersect in ways that challenge our most basic assumptions about existence, identity, and the nature of the cosmos in which we find ourselves. However temporarily, however partially, however mysteriously aware. Traditional quantum mechanics faces what physicists call the measurement problem, one of the most perplexing puzzles in all of science. And understanding this problem is crucial for appreciating why some brilliant minds have been driven to embrace the extraordinary idea of parallel universes. The puzzle begins with a fundamental tension at the heart of quantum theory, between what happens when we're not looking and what happens when we are. Before measurement, quantum mechanics tells us that particles exist in superposition, simultaneously, occupying all possible states according to precise mathematical probabilities. The electron around an atom isn't located in any specific place, but exists as a cloud of possibility, present everywhere. Its wave function has non-zero amplitude. The photon, approaching a beam splitter, doesn't have a predetermined path but travels along all possible routes simultaneously, creating the interference patterns we observe in carefully controlled experiments. This superposition isn't just a mathematical convenience or a reflection of our ignorance about the particle's real properties. Experiments have repeatedly confirmed that quantum systems genuinely exist in multiple states at once when unobserved. The interference patterns in double-slit experiments, the correlations observed in quantum entanglement, the behavior of quantum computers all depend on particles maintaining superposition over time and space. Yet, the moment we try to measure any property of a quantum system, something dramatic and mysterious happens. The superposition vanishes instantly, the wave function collapses, and we observe a single, definite outcome. The electron appears at a specific location. The photon takes one particular path. The quantum system snaps into a classical state with well-defined properties. This transition from quantum to classical behavior presents profound conceptual difficulties. The Schrödinger equation, which governs the evolution of quantum systems, is completely deterministic and reversible. Given the initial state of a quantum system, the equation predicts its future behavior with perfect precision. But this deterministic evolution describes only the smooth change of probabilities over time, the gradual shifting and spreading of wave functions through configuration space. Nothing in the Schrödinger equation accounts for the sudden, irreversible collapse that occurs during measurement. It's as if the fundamental law of quantum mechanics simply stops applying at the moment of observation, replaced by some other, unexplained process that forces nature to choose one outcome from many possibilities. This creates what philosophers of science call the measurement problem. How and why does the transition from quantum superposition to classical definiteness occur? Traditional interpretations of quantum mechanics, like the Copenhagen interpretation developed by Niels Bohr and Werner Heisenberg, acknowledge this mystery but don't really solve it. They simply assert that measurement causes wave function collapse without explaining the mechanism by which this happens. Some versions suggest that consciousness plays a special role, that the act of observation by a conscious mind somehow triggers the collapse. Others propose that interaction with macroscopic measuring devices causes decoherence, the loss of quantum coherence that makes superposition unobservable at large scales. But these explanations raise as many questions as they answer. What constitutes a measurement? How large must a system be before it counts as macroscopic? Does consciousness really play a fundamental role in the structure of reality, or is this just anthropocentric wishful thinking? Where exactly is the boundary between the quantum realm, where superposition applies, and the classical world where objects have definite properties? These questions have puzzled physicists and philosophers for nearly a century without achieving consensus or resolution. Hugh Everett III's many worlds interpretation offers an elegant solution to the measurement problem by denying that wave function collapse ever occurs. In this view, the Schrödinger equation continues to apply always and everywhere, without exception or interruption. When a quantum measurement takes place, the wave function doesn't collapse into a single outcome, but evolves into a superposition of different outcomes, each associated with a different branch of reality. The measuring device, the observer, and indeed the entire universe, split into parallel versions corresponding to each possible result of the measurement. From the perspective of any individual observer in any single branch, it appears that one definite outcome occurred, randomly, but from a global perspective, all outcomes happen simultaneously in different parallel worlds. This solution preserves the fundamental unity and consistency of quantum mechanics, while explaining why measurements appear to yield random results. There's no mysterious collapse mechanism because nothing actually collapses. There's no special role for consciousness because conscious observers are just quantum systems like everything else, subject to the same universal laws. There's no arbitrary boundary between quantum and classical realms, because everything remains quantum at the deepest level. The appearance of classical definiteness emerges from our limited perspective as observers trapped within single branches of the universal wave function. The mathematics work out beautifully in the many worlds interpretation. The probabilities calculated using traditional quantum mechanics correspond exactly to the distribution of outcomes across different branches of the multiverse. If quantum theory predicts a 60% chance of measuring spin-up for an electron, then 60% of the parallel worlds created by the measurement will contain observers who see spin-up results. The randomness isn't fundamental but emerges from the branching structure of reality itself. Each observer experiences a random sequence of measurement outcomes because they can only access one branch of the splitting timeline. But across all branches, the patterns predicted by quantum mechanics are perfectly realized. Yet this elegant solution comes at an extraordinary ontological cost. To solve the measurement problem, the many worlds interpretation requires accepting that reality constantly splits into countless parallel universes, that every quantum event creates new worlds, that the cosmos we inhabit is just one branch of an incomprehensibly vast tree of possibilities. Every radioactive decay, every photon interaction, every molecular collision in your body right now, potentially, spawns new realities where events unfold differently. The theory trades the mystery of wave function collapse for the mystery of parallel world creation, solving one puzzle by embracing an even grander mystery. Critics argue that this cure is worse than the disease, that postulating infinite, unobservable realities to avoid wave function collapse violates the principle of scientific economy. Why accept countless parallel universes, when other interpretations can account for experimental results. Without them, supporters respond that the many worlds interpretation is actually more economical because it requires fewer fundamental assumptions, taking quantum mechanics at face value without adding arbitrary collapse mechanisms or special roles for measurement and place, consciousness. The debate reveals deep tensions in how we think about scientific explanation and the relationship between mathematical formalism and physical reality. Should we follow the mathematics wherever it leads, even if it takes us to parallel worlds beyond observation? Or should we seek explanations that remain within the bounds of what can be experimentally verified? The measurement problem in quantum mechanics forces us to confront these questions directly, challenging our understanding of what science can tell us about the nature of existence. As we drift further into this quantum wonderland of parallel possibilities, remember that we're not just exploring abstract mathematical structures, but grappling with the deepest questions about the nature of reality itself. Whether or not parallel worlds exist, the measurement problem reveals something profound about the strangeness of the quantum realm and the limits of human understanding when confronted with phenomena that transcend our everyday experience of classical objects in space and time. Our second type of parallel universe comes from cosmology, the study of the universe itself on the largest possible scales, and it emerges not from the strange behavior of subatomic particles, but from our best understanding of how the cosmos began, evolved, and continues to expand into an uncertain future. Current theories suggest that our observable universe, that vast sphere of galaxies and dark matter, stretching roughly 14 billion light-years in every direction from Earth, might be just one region in a vastly larger structure, one bubble in an infinite foam of cosmic domains, each with its own history, its own physical laws, and its own possibilities for complexity and life. This extraordinary idea grows out of the theory of cosmic inflation, developed in the 1980s by physicists like Alan Guth, André Linde, and others, to explain some puzzling features of our universe that the standard Big Bang model couldn't account for. The observable universe appears remarkably uniform in temperature and structure across regions that should never have been in contact with each other if the cosmos had expanded at constant speed since its birth. The geometry of space appears perfectly flat, balanced on a knife's edge between eternal expansion and eventual collapse. The density of matter and energy seems fine-tuned to allow for the formation of stars, galaxies, and the complex chemistry necessary for life. Inflation theory proposes that in the earliest moments after the Big Bang, roughly 1036 to 1032 seconds after the universe's birth, space underwent a period of exponential expansion, far more rapid than anything we observe today. During this inflationary epoch, regions of space that were initially in close contact, sharing the same temperature and physical conditions, were stretched apart so rapidly that they lost causal connection with each other. This explains the observed uniformity of the cosmic microwave background radiation, the afterglow of the Big Bang that we see in every direction. What appears to be a remarkable coincidence, that distant regions of space have nearly identical properties, is actually the natural consequence of their shared origin in a much smaller, causally connected region before inflation began. But inflation theory, when taken to its logical conclusions, predicts something far more dramatic than just explaining the uniformity of our observable universe. The quantum fields that drive inflation are subject to quantum fluctuations, random variations that occur on the smallest scales, according to the uncertainty principle of quantum mechanics. In most regions of space, these fluctuations average out, allowing inflation to proceed smoothly and eventually end when the Fortean-Endofortean inflaton field reaches its lowest energy state. But quantum mechanics is inherently probabilistic, and in some regions, random fluctuations will cause the inflaton field to increase rather than decrease, driving those regions into further periods of exponential expansion. This leads to the concept of eternal inflation, where the inflationary process never truly ends, globally, but continues forever in an ever-expanding network of inflating regions, while inflation stops in some areas, allowing for the formation of galaxies and stars and planets. It continues in others, creating new space at an exponential rate. Each region where inflation ends becomes what physicists call a pocket universe, a domain with its own Big Bang, its own evolution, its own physical constants and laws of nature. Our observable universe would be just one such pocket in an infinite multiverse of cosmic bubbles, each containing its own collection of galaxies, each with its own story of stellar formation and planetary evolution. The mathematical description of this eternal inflation scenario suggests that the process has been going on for infinite time and will continue for infinite time into the future. At every moment, countless new pocket universes are being born as inflation ends in different regions, while other regions continue inflating and stretching toward their own eventual transitions to more familiar cosmic expansion. The rate of pocket universe creation is so high that even though individual bubbles are separated by vast distances in the higher dimensional space where inflation occurs, the total number of pocket universes approaches infinity. Each pocket universe would have its own set of physical constants, its own values for fundamental forces and particle masses, determined by the particular way the inflaton field and other quantum fields settled into their lowest energy states when inflation ended in that region. Some pockets might have electromagnetic forces much stronger or weaker than ours, making atoms impossible to form or causing all matter to fly apart. Others might have different ratios of matter to dark matter, different expansion rates, different numbers of spatial dimensions. The landscape of possible pocket universes would encompass every physically consistent set of parameters that the underlying theory allows. This cosmic multiverse would be unimaginably vast and diverse. Most pocket universes would be sterile, dominated by physics that doesn't permit the complex structures necessary for life. In some, matter might be too unstable to form lasting atoms. In others, the fundamental forces might be too weak to bind particles together, or too strong to allow for the nuclear fusion that powers stars. The values of physical constants would be distributed across the multiverse according to the statistical mechanics of the inflation process, with no particular bias toward life-friendly parameters. Yet if the multiverse is truly infinite, containing every possible variation of physical laws and initial conditions, then there would also be countless pocket universes with parameters similar to our own, regions where matter and energy behave in ways that permit the formation of stars, planets, and the complex chemistry that we associate with biological processes. There would be universes nearly identical to ours, differing only in the positions of individual atoms or the outcomes of quantum measurements. There would be worlds where the same physical laws govern slightly different arrangements of matter, perhaps with additional planets in our solar system or different patterns of continental drift on Earth. The implications are both fascinating and deeply unsettling. If the cosmic multiverse contains infinite pocket universes with every possible variation of physical parameters, then somewhere out there exist worlds with every possible arrangement of matter and energy consistent with those parameters. There would be planets identical to Earth except for single molecules, solar systems like ours with subtle differences in planetary orbits, galaxies that mirror our Milky Way with alternate stellar evolution histories. The combinatorial mathematics of infinite possibility would ensure that every story gets told, every possible configuration gets realized, every potential future finds expression in some distant cosmic bubble. This raises profound questions about the uniqueness and significance of our own cosmic circumstances. If there are infinitely many worlds like ours, does our particular history matter? Are we special, or just one random sample from an infinite collection of possibilities? The cosmic multiverse, if it exists, would make our universe simultaneously unique in its exact details and utterly typical as one example among infinitely many similar worlds. We're trapped in our cosmic bubble, unable to see beyond its boundaries, unable to communicate with other pocket universes, or verify their existence through direct observation. The expansion of space itself prevents signals from other bubbles from reaching us, just as our own light can never escape to influence distant regions of the multiverse. We can theorize about this vast cosmic structure, but we remain forever isolated within our own small corner of infinite possibility, wondering about worlds we can mathematically predict but never observe, never visit, never truly know. One of the strongest arguments for a multiverse comes from an uncomfortable observation that has puzzled cosmologists for decades. Our universe seems eerily fine-tuned for life, calibrated with such precision that even tiny changes to fundamental constants would render existence as we know it impossible. The strength of gravity, the mass of electrons, the rate of cosmic 21, expansion, the relative strengths of the nuclear forces. Dozens of fundamental parameters appear to be set within incredibly narrow ranges that allow stars to shine, planets to form, atoms to remain stable, and complex chemistry to unfold over billions of years. Change any of these values by even small amounts, and you get a sterile universe where nothing interesting can happen, where matter either flies apart too quickly for structures to form or collapses so rapidly that stellar nucleosynthesis never has time to create the heavy elements necessary for rocky planets and biological molecules. Consider the cosmological constant, the energy density of empty space that drives the, quote, accelerating expansion of the universe. Current observations suggest this constant has a value, roughly 10^120 times smaller than naive quantum field theory calculations would predict. This represents perhaps the most severe fine-tuning problem in all of physics, a discrepancy so enormous that it's difficult to comprehend why the universe doesn't either collapse immediately under gravitational attraction or expand so rapidly that matter never clumps together into galaxies. Yet somehow, the cosmological constant falls within the incredibly narrow range that permits the formation of cosmic structures while allowing the universe to expand for billions of years, providing the time necessary for stellar evolution and the gradual buildup of chemical complexity. The fine structure constant, which determines the strength of electromagnetic interactions, provides another striking example. If this dimensionless number were significantly larger, electrons would be bound so tightly to atomic nuclei that chemical bonds would be impossible, preventing the formation of molecules and making chemistry as we understand it unworkable. If it were much smaller, electrons would be so loosely bound that atoms would be unstable and matter would have entirely different properties. The observed value falls within a relatively narrow window that allows for stable atoms while permitting the electromagnetic interactions necessary for molecular bonding, stellar fusion, and the complex electromagnetic processes that drive biological metabolism. The ratio of the electromagnetic force to the gravitational force presents yet another puzzle. Gravity is extraordinarily weak compared to electromagnetism, weaker by a factor of about 10^40. But this weakness is crucial for the existence of long-lived stars and planetary systems. If gravity were significantly stronger, stars would burn through their nuclear fuel much more rapidly, shortening their lifetimes to millions or thousands of years instead of the billions required for biological evolution. If gravity were much weaker, stars might never form at all, or they might be so diffuse that nuclear fusion could not ignite in their cores. The observed ratio allows for stellar objects that burn steadily for billions of years while remaining gravitationally bound, systems capable of retaining planetary companions. The masses of fundamental particles also appear to be carefully balanced to permit complex chemistry. If electrons were much heavier, atoms would be smaller and chemical bonds would be very different, potentially preventing the formation of large molecules like proteins and DNA. If protons were slightly heavier relative to neutrons, hydrogen would be unstable and the universe would contain no long-lived light elements, making water impossible and eliminating the most abundant fuel for stellar fusion. If the difference between proton and neutron masses were much larger or smaller, the nuclear processes that synthesize heavy elements in stellar cores would not proceed efficiently, leaving the universe with only hydrogen and helium and no possibility for rocky planets or carbon-based chemistry. Even the number of spatial dimensions appears fine-tuned for complexity and life. In a universe with only two spatial dimensions, complex biological structures would be impossible because circulatory systems and nervous networks could not develop without intersecting and interfering with each other. In universes with four or more spatial dimensions, planetary orbits would be unstable and atoms might not exist in their familiar form because the inverse square law of gravitational and electromagnetic attraction depends critically on three-dimensional geometry. Our universe exists in exactly three spatial dimensions, the unique number that allows for stable orbits, complex atomic structure, and the intricate three-dimensional folding patterns that give biological molecules their functional properties. This apparent cosmic fine-tuning creates a profound puzzle for science because it suggests either extraordinary coincidence or some deeper principle that we don't yet understand. Traditional scientific methodology seeks to explain observations through natural processes and mathematical laws, but the fine-tuning of physical constants seems to require either remarkable luck or some form of selection mechanism that favors life-permitting parameters. The statistical improbability of randomly obtaining values that fall within all the necessary ranges simultaneously is so astronomically small that it challenges our understanding of how the universe could have acquired its observed properties through purely natural processes. Some scientists have proposed anthropic reasoning as a solution. We observe a life-permitting universe precisely because we exist to observe it. In universes where the constants don't permit complex structures or biological processes, there would be no observers to notice the sterility of their cosmic environment. This selection effect means that any observers who exist must necessarily find themselves in a universe compatible with their own existence, regardless of how improbable such a universe might be from a purely statistical perspective. The anthropic principle suggests that the apparent fine-tuning is not really remarkable because we could only exist in universes that permit our existence. But anthropic reasoning by itself doesn't fully resolve the fine-tuning problem because it doesn't explain why life-permitting universes exist at all, only why we happen to find ourselves in one if it does exist. If there is only one universe with randomly selected constants, the probability that it would be life-permitting remains astronomically small, and the anthropic principle provides little comfort. The reasoning becomes more powerful, however, if there are many universes with different constants, because then the existence of at least some life-permitting examples becomes much more likely, and anthropic selection explains why we observe the particular combination of parameters that we do. This is where the multiverse offers a potential resolution to the fine-tuning puzzle. If cosmic inflation creates countless pocket universes with randomly distributed physical constants, then the vast majority would indeed be sterile and lifeless. But a small fraction would have parameters that permit complex chemistry and biological evolution. The absolute number of life-permitting universes could be enormous, even if they represent an infinitesimally small percentage of all possible worlds. Observers like ourselves would necessarily find themselves in this rare subset, not because the universe was designed for life, but because life can only arise in the special circumstances where the constants happen to fall within the narrow ranges that permit complexity. The multiverse thus transforms the fine-tuning problem from an improbable coincidence into a statistical inevitability. Instead of asking why our universe has exactly the right properties for life, we can ask why we observe ourselves in a life-permitting region of a vast multiverse where every possible combination of constants is realized somewhere. The answer becomes straightforward. We exist in such a region because that's the only type of region where observers can exist to ask the question. The apparent design is replaced by selection bias, extraordinary coincidence by statistical necessity. Yet this resolution comes with its own philosophical and scientific challenges. The multiverse, explanation for fine-tuning, is inherently untestable because we cannot observe other pocket universes with different constants to verify that they actually exist. We're trading one mystery for another, replacing the puzzle of cosmic coincidence with the enigma of infinite unobservable realities. Whether this represents genuine scientific progress or merely the substitution of one unfalsifiable hypothesis for another remains a subject of intense debate among physicists, philosophers of science. The theory of eternal inflation, developed by physicists like André Linde and Alan Guth, paints an extraordinary picture of reality that extends the already remarkable concept of cosmic inflation into something even more profound and unsettling. In this view, inflation never truly ends globally, but continues forever in an ever-expanding network of inflating regions, creating new space at an exponential rate, while occasionally spawning pocket universes like our own, where inflation temporarily ceases and more familiar physics takes over. This process has no beginning and no end, creating an infinite hierarchy of cosmic domains nested within each other, like an endless series of Russian dolls, each containing its own collection of bubble universes, each bubble potentially harboring galaxies, stars, planets, and perhaps life. To understand eternal inflation, we must first grasp the dynamics of the inflation process itself. Inflation is driven by a hypothetical quantum field called the inflaton, which exists everywhere in space and has the unusual property that when its value is high, it causes space to expand exponentially. During the inflationary epoch in our universe's early history, this field slowly rolled down from a high-energy state toward its lowest possible energy, and as it did so, the exponential expansion gradually slowed and eventually ended, allowing the more sedate expansion we observe today to take over. The energy stored in the inflaton field was converted into the hot, dense matter and radiation that we call the Big Bang, providing the initial conditions for galaxy formation and stellar evolution. But quantum mechanics tells us that the inflaton field, like all quantum fields, is subject to random fluctuations that occur on the smallest scales of space and time. These fluctuations are usually tiny and average out over larger regions, but occasionally they can be significant enough to push the field value upward rather than downward. In regions where this happens, instead of inflation ending and transitioning to a radiation-dominated universe like ours, the exponential expansion continues, stretching those regions to enormous sizes and creating conditions for further inflationary episodes. Meanwhile, other nearby regions where the fluctuations were smaller or pointed in different directions continue their normal evolution toward the end of inflation. This creates a fractal-like structure where inflating regions give birth to new inflating regions, which in turn spawn their own offspring, while occasionally producing non-inflating bubbles where familiar physics can operate. The mathematics of this process suggest that it's eternal and self-sustaining. Once inflation begins anywhere, it tends to create more inflating volume than it consumes, leading to an exponentially growing network of cosmic domains undergoing exponential expansion. Even though individual regions eventually stop inflating and form pocket universes, the total volume of inflating space continues to increase without bound, ensuring that the process continues forever into the future. The implications of eternal inflation are staggering and difficult to comprehend fully. At every moment, vast numbers of new pocket universes are being created as inflation ends in different regions of the eternally inflating background. Each new pocket universe begins with its own big bang, its own hot, dense initial conditions, its own subsequent evolution toward galaxy formation and stellar nucleosynthesis. The rate of pocket universe creation is so high that even though individual bubbles may be separated by enormous distances in the higher dimensional space where inflation occurs, the total number of pocket universes approaches infinity over the infinite time that the process continues. More remarkably still, eternal inflation appears to produce infinite diversity among the pocket universes it creates. The quantum fluctuations that drive the process are inherently random, and they affect not only the timing of when inflation ends in different regions, but also the values that various quantum fields take on when they settle into their lowest energy states. These field values determine the fundamental constants of physics in each pocket universe: the masses of particles, the strengths of forces, the number of spatial dimensions, and potentially even more exotic properties like the topology of space and the structure of time itself. This means that eternal inflation doesn't just create infinite pocket universes, but infinite variety among them. Some bubbles will have physical constants very similar to our own, differing only in tiny details that might affect the precise timing of stellar evolution or the exact patterns of galaxy formation. Others will have dramatically different physics, with electromagnetic forces much stronger or weaker than ours, gravitational constants that make stellar formation impossible, or particle masses that prevent the formation of stable atoms. Still others might have entirely alien properties that we cannot easily imagine, extraspatial dimensions that remain large instead of curling up on microscopic scales, time that flows in multiple directions, or space that has non-trivial geometric properties affecting the propagation of light and matter. The landscape of possible pocket universes encompasses every physically consistent combination of parameters that the underlying theory allows. Most of these would be sterile and lifeless, dominated by physics that doesn't permit the complex structures necessary for chemistry, biology, and consciousness. But if the total number of pocket universes is truly infinite, then even extraordinarily rare combinations of parameters that permit life would be realized infinitely many times across the eternal inflationary multiverse. There would be countless worlds with conditions suitable for biological evolution, some nearly identical to our own cosmic circumstances, others supporting forms of life based on entirely different chemical and physical principles. The temporal aspects of eternal inflation are particularly mind-bending. The process has been going on for infinite time in the past and will continue for infinite time into the future, constantly, creating new space and new pocket universes. But the notion of time itself becomes problematic in this context because different regions of the multiverse can be inflating at different rates, creating a complex temporal structure where simultaneity is not well defined globally. Events that are contemporaneous in one reference frame may be separated by enormous time intervals when viewed from another perspective, and the very concept of a universal present moment breaks down in the face of exponentially expanding space. This raises profound questions about causality and the relationship between different pocket universes. Although individual bubbles are causally isolated from each other once they form, unable to exchange information or influence each other's evolution, they may have shared causal connections in their past light cones, regions of space-time from which signals could have reached both bubbles before they became separated by exponential expansion. This suggests a kind of cosmic family tree where pocket universes that formed in nearby regions of the eternally inflating background might share common features inherited from their shared causal past, while bubbles that formed in widely separated regions would be essentially independent cosmic experiments. The combination of infinite time, infinite space, and infinite diversity in eternal inflation leads to extraordinary conclusions about the repetition and recurrence of patterns across the multiverse. If every possible arrangement of matter and energy consistent with the physical laws of each pocket universe occurs infinitely often across infinite space and time, then every possible history plays out infinitely many times in various cosmic bubbles. There would be infinitely many worlds, identical to ours down to the quantum level, infinitely many that differ by single particle interactions, infinitely many where historical events unfolded differently due to different random quantum outcomes in the early universe. This statistical mechanics of infinity suggests that eternal inflation, if true, creates a multiverse so vast and diverse that it contains not just every possible physical universe, but every possible story, every possible arrangement of matter, every possible sequence of events that could unfold given the constraints of physical law. We find ourselves in one small corner of this infinite tapestry, observing our particular slice of cosmic history while countless other versions play out, their own variations on the themes of stellar evolution, planetary formation, biological development, and perhaps the emergence of consciousness capable of contemplating its own cosmic context. Yet we remain forever trapped within our own bubble, unable to communicate with other pocket universes or verify their existence through direct observation. The exponential expansion that, to created our cosmic domain, also ensures our permanent isolation from the larger multiverse of which we may be just one infinitesimal part, wondering about infinite worlds we can theoretically predict but never visit, never observe, never truly know beyond the mathematical structures that suggest their existence. Physicist Max Tegmark proposes perhaps the most radical multiverse of all, the mathematical universe hypothesis, an idea so sweeping and fundamental that it challenges our most basic assumptions about the relationship between mathematics and physical reality. If mathematics describes our universe so perfectly, Tegmark argues, perhaps mathematics doesn't just describe reality but actually is reality. Every possible mathematical structure, from simple geometries to complex systems we haven't yet discovered or even imagined, exists as a physical universe somewhere in an infinite mathematical multiverse. Our reality would be just one mathematical structure among infinitely many, distinguished only by the fact that we happen to find ourselves embedded within its particular logical framework. This hypothesis emerges from a deep puzzle that has intrigued scientists and philosophers for centuries. Why is mathematics so unreasonably effective at describing the natural world? The laws of physics can be expressed as elegant mathematical equations that make precise predictions about everything from planetary orbits to quantum interactions. The fundamental constants of nature are dimensionless numbers that appear in mathematical relationships, governing the behavior of matter and energy. Even the most abstract branches of pure mathematics, developed with no thought of practical application, often turn out to have unexpected relevance to physical phenomena discovered decades or centuries later. Complex numbers, originally dismissed as mathematical curiosities, became essential for quantum mechanics. Non-Euclidean geometries, once considered purely theoretical exercises, provided the mathematical foundation for general relativity. Tegmark's radical answer to this puzzle is that mathematics is not a human invention for describing an independently existing physical world, but is instead the fundamental substance from which all realities are constructed. In this view, what we call physical properties like mass, charge, and momentum are not intrinsic features of matter, but rather mathematical relationships within abstract structures. A particle is not a little ball with mathematical properties, but a mathematical object embedded in a larger mathematical framework that we interpret as space-time and quantum fields. The reason mathematics works so well for describing nature is that nature is mathematics, viewed from the inside by conscious subsystems of the Pruli, mathematical structure itself. This mathematical universe hypothesis implies that every self-consistent mathematical structure corresponds to a genuine physical reality. Simple structures like Euclidean geometry would exist as universes with perfectly flat space and trivial dynamics. More complex structures, incorporating differential equations and symmetry groups, would correspond to universes with rich physics supporting matter, energy, and evolution over time. Our own universe would be one particular mathematical structure, perhaps something like a four-dimensional manifold with specific gauge symmetries and field equations that generate the standard model of particle physics and general relativity. But the implications extend far beyond familiar physics. If every mathematical structure exists as a physical reality, then there would be universes based on different numbers of dimensions, different algebraic structures, different logical foundations altogether. Some might be discrete rather than continuous, built from networks of abstract relationships rather than smooth, space-time geometries. Others might have temporal structures completely unlike our linear progression from past to future, with multiple time dimensions or cyclical causal loops that have no beginning or end. Still others might be based on mathematical systems so alien to our with experience that we lack. Even conceptual frameworks for imagining what existence within them would be like. The mathematical multiverse would include all possible variations on familiar themes, as well as structures that push beyond the boundaries of conventional physics. There would be universes where the roles of space and time are reversed, where quantum mechanics operates according to different probability rules, where symmetries exist that have no analog in our world. Mathematical structures based on non-classical logics might support realities where the law of excluded middle doesn't apply, where statements can be simultaneously true and false, where causation follows patterns that violate our most basic intuitions about how events relate to each other. This raises fascinating questions about consciousness and observation within the mathematical multiverse. If conscious beings like ourselves are patterns of information processing within mathematical structures, then every structure complex enough to support self-aware subsystems would contain observers experiencing their particular mathematical reality from the inside. These observers would develop concepts of physics, chemistry, and biology based on the mathematical relationships that govern their universe, never suspecting that they are themselves mathematical objects embedded in abstract logical frameworks. Some mathematical structures might support forms of consciousness radically different from biological intelligence. Digital beings might exist as computational processes within discrete mathematical networks. Geometric consciousness might emerge from topological relationships in high-dimensional spaces. Quantum awareness might arise from superposition states in complex Hilbert spaces that bear no resemblance to the classical world we inhabit. Each type of consciousness would experience its mathematical universe as concrete physical reality, developing sciences and philosophies appropriate to its particular logical environment. The mathematical universe hypothesis also suggests interesting possibilities for communication and travel between different mathematical realities. If some mathematical structures share common substructures or can be mapped onto each other through mathematical transformations, then information or even conscious beings, might potentially move between different mathematical universes. What we call physics might be just one layer of mathematical relationships within larger structures that encompass multiple physical realities as special cases, or limiting behaviors. Yet this radical vision faces significant philosophical and scientific challenges. Critics argue that not all mathematical structures are equally real or physically meaningful, that some distinction must be made between abstract mathematical objects and concrete physical systems. The hypothesis also struggles with the problem of infinite regress. If every mathematical structure exists as a physical reality, what determines which mathematical framework we use to describe the multiverse itself? Are we trapped within mathematical structures that limit our ability to comprehend the full scope of mathematical reality? There's also the question of what it means for a mathematical structure to exist as a physical universe. Traditional notions of physical existence involve concepts like matter, energy, and space-time that may not apply to abstract mathematical objects. The mathematical universe hypothesis asks us to abandon these familiar concepts in favor of a purely structural view of reality where existence is equivalent to mathematical consistency and logical coherence. The hypothesis remains highly speculative and difficult to test experimentally, but it offers a profound perspective on the relationship between mind and mathematics, between abstract truth and physical reality. If Tegmark is correct, then every equation we write, every theorem we prove, every mathematical structure we explore is not just a description of possible worlds, but a glimpse into actual realities existing somewhere in the vast landscape of mathematical truth. We are mathematical beings embedded in mathematical reality, using mathematical minds to explore the infinite mathematical multiverse, of which we are one small but significant part. Here's where our cosmic journey encounters serious turbulence. How do you prove the existence of something you can never observe? This fundamental question strikes at the heart of all multiverse theories and reveals a deep tension between mathematical elegance and empirical science that has divided the physics community for decades. By definition, parallel universes exist beyond our observational horizon, separated from us by quantum branching, cosmic inflation, or the abstract boundaries between mathematical structures. We cannot visit quantum alternate realities where different measurement outcomes occurred. We cannot peek beyond our cosmic bubble to observe other pocket universes with different physical constants. We cannot step outside mathematics to examine mathematical structures from an external perspective. This places multiverse theories in a peculiar and controversial position scientifically, where some of our most successful theoretical frameworks predict the existence of phenomena that may be forever beyond experimental verification. The problem runs deeper than simple observational limitations. In traditional science, theories gain credibility through their ability to make testable predictions about measurable phenomena. We accept the existence of electrons not because we can see them directly, but because atomic theory makes precise predictions about chemical reactions, electrical conduction, and spectroscopic phenomena that can be verified in laboratories around the world. Similarly, we believe in black holes not because we can visit them, but because general relativity predicts their properties and behavior in ways that match astronomical observations of gravitational lensing, orbital dynamics, and recently even direct imaging of event horizons. But multiverse theories present a different kind of challenge because they emerge naturally from our best physical theories, while making claims about realities that seem fundamentally unobservable. The many worlds interpretation of quantum mechanics arises from taking the Schrödinger equation seriously and applying it universally, but it predicts the existence of parallel branches that are causally disconnected from our own experience. Eternal inflation follows naturally from the dynamics of quantum fields in curved space-time, but it suggests the existence of countless pocket universes beyond our causal horizon. The mathematical universe hypothesis provides an elegant answer to the unreasonable effectiveness of mathematics, but it postulates the existence of abstract structures that have no clear connection to empirical observation. This puts multiverse theories in what philosophers of science call the demarcation problem, the question of what distinguishes genuine science from mere speculation or pseudoscience. Traditional criteria for scientific theories include falsifiability, the ability to make predictions that could potentially be proven wrong by experimental evidence. But if multiverse theories predict the existence of things that cannot be observed even in principle, how can they ever be falsified? Critics argue that this makes them unscientific, interesting mathematical exercises rather than genuine physics. They worry that accepting untestable theories opens the door to all kinds of unfounded speculation and undermines the empirical foundation that gives science its reliability and authority. Supporters of multiverse theories respond with several arguments. First, they point out that many successful scientific theories have postulated unobservable entities that were later vindicated by indirect evidence or technological advances. Atoms were theoretical constructs for centuries before electron microscopy made them visible. Electromagnetic fields were purely mathematical abstractions before radio waves revealed their physical reality. Black holes were exotic solutions to Einstein's equations before astronomical observations confirmed their existence. Perhaps multiverse theories will similarly transition from theoretical speculation to established science as our understanding and capabilities advance. Second, they argue that multiverse theories should be judged not as isolated hypotheses, but as consequences of broader theoretical frameworks that do make testable predictions. Quantum mechanics and general relativity have been verified to extraordinary precision across countless experiments and observations. If these theories naturally predict the existence of parallel universes, then rejecting multiverses might require abandoning our most successful descriptions of nature. The choice isn't between testable and untestable theories, but between accepting the full implications of our best theories or arbitrarily limiting them to avoid uncomfortable conclusions. Third, supporters contend that the traditional emphasis on direct observability is too restrictive. For modern physics, which routinely deals with phenomena at scales and energies far removed from everyday experience, we cannot directly observe quarks inside protons, but we infer their existence from particle collision experiments. We cannot directly measure the curvature of space-time, but we verify general relativity through its effects on light and matter. Science has always relied on indirect inference and theoretical reasoning to extend our understanding beyond the limits of direct perception. The debate also involves deeper questions about the nature of scientific explanation and the role of mathematical beauty in theory construction. Many physicists are guided by aesthetic criteria like elegance, symmetry, and mathematical simplicity when developing new theories, believing that nature's fundamental laws should have a certain mathematical beauty and logical coherence. Multiverse theories often score high on these aesthetic measures, providing unified explanations for seemingly unrelated phenomena and resolving conceptual puzzles that have long troubled theorists. But critics worry that aesthetic preferences can mislead scientists into accepting theories that feel intellectually satisfying but have no basis in reality. The history of science includes many beautiful theories that turned out to be wrong, from the crystalline celestial spheres of ancient astronomy to the elegant, steady-state cosmology of the mid-20th century mathematical. Beauty alone is not sufficient evidence for physical truth, and theories that cannot be tested risk becoming elaborate mathematical fantasies disconnected from the empirical world. The problem of evidence for multiverse theories also raises questions about the nature of explanation in science. Even if we cannot directly observe parallel universes, multiverse, theories claim to explain puzzling features of our own universe, like the fine-tuning of physical constants or the randomness of quantum measurements. But explanation without prediction can become circular reasoning, where we postulate unobservable entities to account for observed phenomena while having no independent way to verify that those entities actually exist. This philosophical uncertainty creates a peculiar situation where brilliant physicists and mathematicians develop increasingly sophisticated theories about vast, unobservable realities, while remaining unable to definitively establish whether those realities exist outside their equations. The mathematics is rigorous, the logic is sound, the theoretical frameworks are elegant and internally consistent, but the connection to physical truth remains tantalizingly ambiguous. We find ourselves in the strange position of having detailed mathematical descriptions of infinitely many worlds we may never be able to visit, observe, or definitively prove exist beyond the abstract realm of theoretical possibility. While we cannot directly observe parallel universes, some theories suggest indirect ways to detect their influence, tantalizing possibilities that might allow us to glimpse evidence of other realities without ever visiting them or communicating with their inhabitants. These approaches remain highly speculative and controversial, representing the cutting edge of theoretical physics, where rigorous mathematics meets the practical limitations of what can actually be measured in our universe. The evidence, such as it is, remains ambiguous and open to multiple interpretations, creating a scientific landscape where we might be seeing genuine glimpses of parallel worlds or simply patterns that have nothing to do with multiverses but reflect other, more mundane aspects of physics we don't yet fully understand. In the many worlds interpretation of quantum mechanics, some physicists have proposed that quantum interference effects might preserve subtle signatures of parallel realities. When quantum systems maintain coherence over extended periods, they can exhibit interference, patterns that depend on the full superposition of all possible states, not just the single outcome we observe after measurement. These interference effects might carry information about the parallel branches that split off during quantum evolution, like echoes from alternate histories that remain detectable in carefully controlled experiments. Quantum computers, which exploit superposition to perform calculations impossible for classical systems, might be accessing computational resources from parallel worlds where different quantum states are realized. The theoretical basis for these ideas remains contentious, with critics arguing that decoherence effects make it impossible to maintain the quantum coherence necessary to detect signatures from parallel branches. Once a quantum system interacts with its environment, the different branches of the wave function become causally disconnected and cannot interfere with each other in measurable ways. But some researchers continue to explore whether extremely sensitive experiments might detect subtle violations of classical probability theory or other anomalies that could indicate the influence of parallel quantum realities. In cosmology, scientists have looked for patterns in the cosmic microwave background radiation that might reveal collisions with other pocket universes in the multiverse. If our cosmic bubble occasionally bumped into neighboring bubbles during the early stages of cosmic expansion, these collisions might have left distinctive signatures in the temperature fluctuations of the background radiation. Some researchers have claimed to detect circular patterns or other anomalies in cosmological data that could represent the aftermath of such collisions, but these claims remain disputed and have not achieved widespread acceptance in the scientific community. The search for evidence of bubble collisions faces fundamental challenges because any such events would have occurred in the distant past when our universe was much smaller and denser. The signatures would be extremely faint and difficult to distinguish from other sources of cosmological fluctuations. Moreover, The statistical analysis required to identify these patterns is complex and susceptible to false positives, where random noise in the data creates apparent patterns that have no physical significance. The current state of evidence for bubble collisions remains inconclusive at best. Another approach involves looking for anomalies in the values of fundamental constants that might indicate our universe's special properties within a larger multiverse. If physical constants are randomly distributed across different pocket universes, as eternal inflation theories suggest, then precise measurements of these constants in our universe might reveal patterns or relationships that are unlikely to arise by chance. Some physicists have noted curious numerical relationships between fundamental constants, like the apparent fine-tuning of the cosmological constant or unexpected connections between particle masses and force strengths. However, distinguishing genuine evidence for multiverse structure from coincidental numerical relationships proves extremely difficult. The human tendency to find patterns in random data, combined with the flexibility of theoretical models that can accommodate a wide range of observations, makes it easy to construct multiverse explanations for almost any set of measured values. Without independent ways to verify the existence of other universes with different constants, these observations remain suggestive at best, rather than compelling evidence for parallel realities. Quantum gravity theories, particularly string theory, offer another potential avenue for multiverse evidence through their predictions about the mathematical structure of physical law. String theory suggests that our familiar three-dimensional space might be embedded in a higher dimensional framework where additional spatial dimensions are curled up on microscopic scales. If these extra dimensions have different geometries in different regions of the multiverse, they might affect observable physics in subtle but measurable ways through their influence on particle properties and force strengths. Experiments at high-energy particle accelerators might potentially detect signatures of extra dimensions or other stringy phenomena that could provide indirect evidence for the kind of mathematical structure predicted by multiverse theories. However, these signatures would not directly prove the existence of other universes, but would only confirm that our universe has the mathematical properties that multiverse theories suggest. The logical chain from detecting extra dimensions to proving parallel realities remains long and uncertain. Perhaps the most intriguing possibility involves the anthropic principle and the apparent fine-tuning of physical constants for life. If our universe exists within a vast multiverse where constants vary randomly across different domains, then the observation that our local constants permit complexity in life might itself be a form of evidence. The statistical argument runs as follows. If there is only one universe with randomly chosen constants, the probability of obtaining life-permitting values is astronomically small. But if there are countless universes with different constants, then the existence of at least some life-permitting examples becomes much more likely, and observers like ourselves would necessarily find themselves in such regions. This anthropic reasoning remains controversial because it's difficult to calculate meaningful probabilities without knowing the underlying mechanism that determines how constants are distributed across the multiverse. Different assumptions about this distribution lead to different predictions, and there's no clear way to choose between them based on current evidence. Moreover, the anthropic argument doesn't directly prove that other universes exist, but only suggests that their existence would explain the apparent coincidence of life-friendly constants in our cosmic neighborhood. The search for multiverse evidence thus remains an active but inconclusive area of research, where theoretical motivation outpaces observational confirmation. We have sophisticated mathematical frameworks that naturally predict parallel universes, and we have some tentative observational anomalies that might be consistent with multiverse models, but we lack the clear, unambiguous evidence that would convince skeptics and establish multiverse theories as accepted science. The scientific jury remains out, and may remain out for a very long time, leaving us in the peculiar position of having detailed, theoretical descriptions of infinite realities that we may never be able to definitively prove exist beyond the abstract realm of mathematical possibility. The anthropic principle offers another lens through which to view parallel universes, and it represents one of the most philosophically challenging and scientifically contentious approaches to understanding our cosmic situation. This principle observes that any universe capable of being observed must, by definition, be capable of supporting observers, a statement that seems almost tautologically obvious until you consider its implications for how we interpret the apparent fine-tuning of physical constants and the improbable conditions that permit complex chemistry, biological evolution, and conscious intelligence. The anthropic reasoning suggests that we shouldn't be surprised to find ourselves in a life-permitting universe, regardless of how statistically unlikely such a universe might be, because we could only exist to ask questions about cosmic fine-tuning in worlds where the conditions actually permit our existence. This line of thinking comes in several varieties, each with different implications for multiverse theories and scientific methodology. The weak anthropic principle simply states that we observe the universe to have properties compatible with our existence, because we exist to observe it. This is relatively uncontroversial as a statement about observational selection effects, though it doesn't explain why life-permitting universes exist in the first place. The strong anthropic principle goes further, suggesting that the universe must have properties that allow life to develop within it at some point during its history. This stronger version borders on teleological reasoning and is generally rejected by scientists because it seems to imply that the universe was designed or constrained specifically to produce observers. The participatory anthropic principle, advocated by physicist John Wheeler, proposes that observers play a fundamental role in bringing the universe into existence through the act of observation, drawing on interpretations of quantum mechanics where measurement appears to retroactively determine the properties of quantum systems. This version ventures into highly speculative territory about the role of consciousness in physical law and remains far from mainstream scientific acceptance. Most scientists prefer the weak anthropic principle as a useful tool for thinking about observational bias while avoiding the stronger metaphysical claims about cosmic purpose or the special role of consciousness. The anthropic principle becomes particularly relevant in the context of multiverse theories because it potentially resolves the fine-tuning problem without requiring intelligent design, extraordinary coincidence. If countless universes exist with randomly distributed physical constants, as eternal inflation theories suggest, then the vast majority would indeed be sterile and lifeless, incapable of supporting the complex chemistry necessary for biological processes. But if the total number of universes is sufficiently large, then some fraction, however small, would have constants that fall within the narrow ranges, permitting atomic stability, stellar nucleosynthesis, planetary formation, and evolutionary processes. The absolute number of life-permitting universes could be enormous, even if they represent an infinitesimally small percentage of all possible worlds. In an infinite multiverse, even probabilities approaching zero can be realized infinitely many times, ensuring that observers like ourselves not only can exist but must exist in countless cosmic domains. The anthropic principle, then, explains why we find ourselves observing apparently fine-tuned conditions. We necessarily inhabit one of the rare regions where the constants permit complex structures and conscious observers, not because the universe was designed for life, but because life can only arise in the special circumstances where physics permits its existence. Critics argue that anthropic reasoning is a cop-out that explains away fine-tuning without making testable predictions about observable phenomena, instead of seeking deeper physical principles that might explain why constants have their observed values. Anthropic arguments simply assert that we observe life-friendly values because we exist to observe them. This approach seems to abandon the traditional scientific goal of finding fundamental explanations for natural phenomena in favor of statistical arguments about observer selection effects that cannot be independently verified. Moreover, anthropic reasoning faces the reference class problem. When calculating the probability of observing particular conditions, what should be included in the statistical sample? Should we consider all possible observers, all carbon-based life forms, all intelligent species, or some other category? Different choices lead to different probability calculations and different predictions about what we should expect to observe. Without a clear way to define the reference class, anthropic arguments become dependent on arbitrary assumptions about the nature of observers and the conditions necessary for their existence. The measure problem in eternal inflation creates additional difficulties for anthropic reasoning. If inflation creates infinite space containing infinite observers in infinite universes, then conventional probability calculations break down because we're dividing infinite quantities. Different ways of regularizing these infinities lead to different predictions about the relative frequency of various physical constants across the multiverse, making it difficult to determine whether our observed values are typical or atypical within the broader ensemble of pocket universes. Some physicists have attempted to make anthropic reasoning more rigorous by developing specific models for how physical constants might vary across the multiverse and calculating the point resulting distribution of life-permitting regions. String theory, for example, suggests that the landscape of possible vacuum states might have a complex structure where some regions are more likely to produce observers than others. If this landscape can be mapped mathematically, it might be possible to make testable predictions about the values of constants we should expect to observe in our cosmic neighborhood. These approaches remain highly speculative and depend on theoretical frameworks like string theory that are themselves unverified by experimental evidence. The connection between abstract mathematical structures and concrete predictions about observable constants remains tenuous, and different models often make contradictory predictions about what constitutes typical values within the multiverse. The field of anthropic reasoning in cosmology thus remains divided between those who see it as a promising approach to understanding cosmic fine-tuning and those who view it as an abandonment of traditional scientific methodology. The anthropic principle also raises profound questions about the meaning and significance of individual existence within a multiverse framework. If there are infinitely many observers like ourselves making similar observations in similar cosmic conditions, does our particular andations in similar cosmic conditions perspective have any special significance? Are we unique individuals experiencing a singular reality, or are we just one instance of a pattern repeated infinitely, often across the multiverse? These questions touch on deep issues in philosophy of mind about personal identity, consciousness, and the relationship between subjective experience and objective reality. The implications extend to practical questions about how we should conduct science and make decisions in a multiverse context. If every possible outcome occurs somewhere in the ensemble of parallel realities, does it matter which particular branch of reality we happen to inhabit? Should scientific theories be judged by their success in our observed universe or by their performance across the entire multiverse? These questions remain largely unanswered and may ultimately be unanswerable, but they illustrate how multiverse theories challenge not just our understanding of cosmic structure, but our basic assumptions about knowledge, causation, and the meaning of scientific inquiry itself. Quantum computers offer an intriguing window into parallel universe possibilities, suggesting that these remarkable devices might provide our first practical glimpse of multiverse phenomena through their extraordinary computational capabilities. These machines exploit quantum superposition to perform calculations in ways classical computers cannot, manipulating quantum bits that exist simultaneously in multiple states until measurement forces them to collapse into definite values. Some interpretations of quantum computing suggest that these devices literally borrow computational power from parallel universes, accessing the processing capabilities of countless alternate realities where different quantum states are realized simultaneously across the branches of the universal wave function. The theoretical foundation for this interpretation emerges from the many worlds framework of quantum mechanics, where quantum computers would not simply manipulate abstract superposition states, but would coordinate calculations across multiple branches of reality. When a quantum computer factors large numbers using Shor's algorithm, it might be exploiting parallel versions of itself in alternate universes where different trial factors are tested simultaneously. The exponential speed-up that quantum computers can achieve for certain problems would result from accessing exponentially many parallel computational resources, with each branch of the multiverse contributing to the overall calculation before the results are combined through quantum interference effects. Consider the operation of a quantum computer attempting to solve a complex optimization problem or search through a vast database. In the classical world, such tasks require examining possibilities sequentially, checking each potential solution one by one until the correct answer is found. But quantum computers can maintain superpositions of all possible solutions, simultaneously, effectively exploring every branch of the solution space in parallel. The many worlds interpretation suggests that this parallelism is not merely mathematical abstraction, but reflects genuine parallel processing occurring across multiple realities. Each quantum bit in the computer exists in superposition, simultaneously representing 0 and 1 in different branches of the universal wave function. When multiple qubits are entangled together, they create vast superposition spaces where exponentially many computational states coexist. A quantum computer with just a few hundred qubits can access computational spaces larger than the number of atoms in the observable universe, suggesting that the processing power comes from regions of reality far beyond our direct experience. If the many worlds interpretation is correct, these computations would be distributed across parallel universes, where different combinations of qubit states are realized. The process of quantum error correction, essential for building practical quantum computers, provides another perspective on potential multiverse connections. Quantum states are fragile and easily disrupted by environmental interference, but error correction schemes can detect and fix these disruptions by encoding information redundantly across multiple qubits. Some theorists suggest that error correction might work by accessing information from parallel branches where the same quantum state evolved differently, using correlations across the multiverse to restore corrupted data and maintain computational coherence. Quantum algorithms like Grover's search algorithm demonstrate this parallel processing most clearly. When searching through an unsorted database, a classical computer must examine entries one by one, requiring time proportional to the database size. But Grover's algorithm can find the correct entry in time proportional to the square root of the database size, a quadratic speed-up that classical computers cannot match. The many worlds interpretation suggests that this advantage comes from simultaneously searching different portions of the database in parallel universes, with quantum interference effects combining the results to identify the correct answer. The implications extend beyond mere computational efficiency to questions about the nature of information and computation itself. If quantum computers access parallel processing power from alternate realities, then information processing becomes a fundamentally multiverse phenomenon, with computational resources distributed across vast networks of parallel worlds. The results of quantum calculations would not emerge from isolated classical systems, but from collaborative efforts spanning multiple branches of reality, each contributing to the final outcome through subtle quantum mechanical correlations. However, this interpretation remains highly speculative and contentious within the physics community. Many quantum computing researchers prefer more conservative interpretations that avoid postulating parallel universes, arguing that quantum speedup can be understood purely in terms of mathematical superposition without requiring ontological commitments to alternate realities. They point out that quantum computers, despite their exotic capabilities, still operate according to well-understood principles of quantum mechanics that don't necessarily require multiple worlds to explain their behavior. The debate touches on fundamental questions about the relationship between mathematical, formalism, and physical reality in quantum mechanics. When quantum computers manipulate superposition states to achieve computational advantages, are they exploiting abstract, mathematical structures or accessing genuine physical resources distributed across parallel worlds? The answer depends crucially on which interpretation of quantum mechanics proves correct, and this remains one of the deepest unsolved problems in theoretical physics. Experimental tests of quantum computing might eventually provide indirect evidence for or against multiverse interpretations. If quantum computers achieve computational capabilities that seem to exceed what should be possible within a single universe, this might support the many worlds interpretation. Conversely, if quantum computing remains limited by the resources available in our observable universe, this might favor more conservative interpretations of quantum mechanics. However, distinguishing between these possibilities requires careful analysis of computational complexity theory and may not provide definitive answers about the nature of parallel realities. The relationship between quantum computing and consciousness adds another layer of complexity to these questions. Some researchers suggest that biological systems might exploit quantum effects for information processing, potentially accessing parallel computational resources through quantum coherence in neural microtubules or other biological structures. If consciousness itself involves quantum computation, then human thought and decision-making might be distributed across parallel branches of reality, with our subjective experience representing just one thread in a vast tapestry of parallel cognitive processes. This speculation remains far from mainstream scientific acceptance and faces significant challenges from our understanding of biological systems and the role of decoherence in warm, noisy environments like living cells. But it illustrates how quantum computing opens new possibilities for thinking about the relationship between mind and multiverse, between information processing and the fundamental structure of reality. Whether quantum computers provide windows into parallel worlds or simply exploit clever mathematical tricks, they represent humanity's first practical technology for manipulating quantum mechanical phenomena on macroscopic scales. As quantum computing technology continues to advance, we may gain new insights into the nature of quantum mechanics and its implications for our understanding of reality. The devices we're building today might serve as laboratories for exploring some of the deepest questions in physics, potentially providing the first empirical tests of multiverse theories through their unprecedented ability to manipulate quantum superposition and entanglement. Every quantum calculation might be a collaboration between parallel worlds, a practical consequence of the many worlds interpretation that we're only beginning to explore and understand. String theory, physics' ambitious attempt to unify all fundamental forces into a single mathematical framework, predicts a vast landscape of possible universes that makes our cosmic home just one example among an almost incomprehensibly large number of alternatives. The theory suggests that our familiar particles like electrons and quarks are not point-like objects, but rather tiny vibrating strings existing in a space-time that has more than the four dimensions we directly experience. These strings can vibrate in countless different patterns across multiple spatial dimensions, and each vibration mode corresponds to different particles, forces, and physical properties that we observe in our universe. The mathematical structure of string theory requires additional spatial dimensions beyond the three we can move through and the one-time dimension that marks the passage of events. Depending on the specific version of string theory, the total number of dimensions ranges from 10 to 26, with the extra dimensions curled up or compactified on scales so small that we cannot detect them directly. The geometry of these hidden dimensions determines how the strings vibrate and thus controls the properties of particles and forces that emerge in the four-dimensional world we inhabit. This leads to what string theorists call the landscape problem. There appear to be an enormous number of ways that the extra dimensions can be arranged and compactified, each corresponding to a different possible universe with its own set of physical laws. Early estimates suggested there might be around 10,500 different possible compactifications, a number so vast that it challenges human comprehension. To put this in perspective, the total number of atoms in the observable universe is estimated to be around 1080, making the string theory landscape larger by a factor that itself requires scientific notation to express meaningfully. Each point in this landscape represents a different solution to the equations of string theory, corresponding to a universe where the extra dimensions have a particular geometric configuration, and where strings vibrate according to specific patterns that determine particle masses, force strengths, and other fundamental constants. Some regions of the landscape might produce universes very similar to our own, with electrons, protons, photons, and the familiar forces of electromagnetism and gravity. Other regions might yield universes with completely different particle spectra, exotic forces that have no analog in our experience, or even spacetimes with different numbers of macroscopic dimensions. The landscape encompasses universes where the strong nuclear force might be thousands of times stronger or weaker than in our world, making atomic nuclei either impossible to form or so tightly bound that nuclear fusion cannot occur in stellar cores. It includes possibilities where the electromagnetic force has completely different properties, perhaps making chemistry impossible, or creating new types of atomic structures that we cannot imagine. Some regions might correspond to universes where gravity operates according to modified rules, with different long-range behavior that would drastically alter the formation and evolution of galaxies, stars, and planetary systems. Most remarkably, the landscape might include universes with different numbers of macroscopic spatial dimensions. While string theory typically predicts that only 3 spatial dimensions remain large while others remain microscopic, some solutions might allow for universes with 2 large spatial dimensions, or 4 or more. These alternate geometries would create realities so foreign to our experience that we lack adequate conceptual frameworks for understanding what existence would be like within them. Physics, chemistry, and biology, as we know them, depend crucially on the three-dimensional nature of space, and alternate dimensionalities would require completely different organizing principles for matter, energy, and information. The temporal structure of the landscape also allows for exotic possibilities. Some string theory solutions might correspond to universes with multiple time dimensions or with closed time-like curves that permit various forms of time travel. Others might have discrete rather than continuous time, where the universe evolves in discrete steps rather than flowing smoothly from moment to moment. Still others might have temporal dimensions that are compactified like some of the spatial dimensions, creating universes with fundamentally different causal structures than anything we can directly comprehend. If string theory is correct, and if all these mathematical possibilities correspond to actual physical realities, then parallel universes become not just possible but inevitable consequences of the theory's fundamental structure. The landscape would represent a multiverse of unimaginable scope and diversity, containing every possible variation on the themes of matter, energy, space, and time that the underlying mathematical framework allows. Our universe would be just one point in this vast parameter space, distinguished only by the particular combination of compactification, geometry, and string vibration patterns that happen to characterize our local region of the landscape. But the landscape also creates significant challenges for string theory as a scientific framework. If there are 500 different possible universes predicted by the theory, how can we determine which one corresponds to our observed reality? Traditional scientific theories make specific predictions that can be tested through experiment and observation, but a theory that predicts almost every conceivable possibility provides little guidance about what we should expect to observe in our particular cosmic circumstances. This leads to what critics call the landscape problem, or the string theory swampland conjecture. They argue that a theory capable of producing almost any imaginable universe cannot really be considered predictive science, but becomes instead a mathematical framework so flexible that it can accommodate virtually any experimental result. If string theory can explain any possible set of physical constants and natural laws, then it explains nothing specifically about why our universe has the particular properties we observe, rather than countless alternatives. String theorists have responded to these criticisms in various ways. Some argue that anthropic reasoning might help select the subset of landscape solutions that are compatible with the existence of observers like ourselves, potentially making testable predictions about the range of physical constants we should expect to find. Others suggest that dynamical processes during cosmic evolution might preferentially select certain regions of the landscape, making some types of universes more common than others, even if all mathematical possibilities are theoretically realized somewhere. The landscape also intersects with cosmological theories about eternal inflation and the multiverse. If cosmic inflation creates countless pocket universes, as some theories suggest, and if string theory correctly describes the fundamental physics governing these domains, then different pockets might explore different regions of the string landscape. Each inflationary bubble would undergo its own process of compactification and symmetry breaking, potentially settling into different landscape solutions and creating a cosmological multiverse with the vast diversity that string theory mathematics suggests. This combination of eternal inflation and string theory landscape could produce a multiverse that encompasses not just different values of familiar physical constants, but entirely different types of physics, operating according to principles we have never encountered. The result would be a reality of such scope and strangeness that our universe, for all its galaxies and complexity and billions of years of evolution, would represent just one tiny sample from an infinite library of possible worlds, each following its own mathematical rules and supporting its own forms of structure, complexity, and perhaps even consciousness adapted to utterly alien physical principles. A modern twist on parallel universes comes from the simulation hypothesis, popularized by philosopher Nick Bostrom in the early 2000s, which suggests that what we experience as reality might actually be an artificial simulation running on powerful computers operated by some advanced civilization. This idea represents a departure from the physics-based multiverse theories we've explored, instead proposing that parallel realities might be digital rather than quantum or cosmological, created by intelligence rather than emerging from natural processes. If advanced civilizations routinely develop the computational power to run detailed simulations of their history, complete with conscious beings who believe themselves to be real, then most conscious entities would actually be simulated rather than biological, living in parallel digital worlds alongside countless other virtual realities. The simulation hypothesis begins with a simple observation about technological progress. Our own computing power has increased exponentially over the past several decades, and we're already creating increasingly sophisticated simulations of everything from weather patterns to entire virtual worlds populated by artificial intelligence. If this trend continues for thousands or millions of years, future civilizations might develop computers capable of simulating entire universes complete with galaxies, planets, ecosystems, and conscious beings who experience their simulated world as completely real and never suspect their digital constructs. Bostrom's argument takes the form of a trilemma. proposing that at least one of three statements must be true. Either intelligent civilizations almost never reach technological maturity, or technologically mature civilizations almost never run ancestor simulations, or we are almost certainly living in a computer simulation. The logic runs as follows. If civilizations frequently reach advanced technological capabilities, and if they choose to use some of their computational resources to run detailed historical simulations, then the number of simulated beings would vastly outnumber the original biological entities. A single advanced civilization might run millions of historical simulations, each containing billions of conscious entities, creating a ratio where simulated minds outnumber real ones by enormous factors. The implications extend far beyond science fiction speculation into fundamental questions about the nature of consciousness, identity, and reality itself. If we are simulations, then our entire experience of physical existence, our sense of embodiment, our perception of space and time, would be artificial constructs generated by information processing, rather than direct interaction with matter and energy. Our memories, our relationships, our entire personal histories might be programmed rather than lived, data structures in a computer rather than patterns of neurons in biological brains. This raises profound questions about what it would mean to be a simulated conscious being. Would simulated consciousness be qualitatively different from biological consciousness? Or would the substrate independence of information processing make simulated experiences indistinguishable from real ones? If consciousness is fundamentally about information, integration, and processing, as some theories suggest, then simulated minds might be just as real and morally significant as biological minds, regardless of whether they're implemented in carbon or silicon, cells or circuits. The simulation hypothesis also suggests the existence of vast hierarchies of nested realities. If we are simulations created by some advanced civilization, that civilization might itself be a simulation running on even more powerful computers operated by still more advanced beings. This creates the possibility of infinite recursive simulations, realities within realities extending upward through levels of increasing computational sophistication. Each level might contain countless parallel simulations exploring different historical scenarios, alternative evolutionary paths, or variations on the basic parameters governing physics and chemistry. Different simulation projects might focus on different aspects of reality or different time periods, creating a vast library of parallel digital worlds. Some simulations might explore counterfactual histories, asking what would have happened if certain historical events had unfolded differently. Others might test alternative physical laws or evolutionary scenarios. Still, others might serve as entertainment or educational tools for beings whose motivations and interests we cannot fathom. We might be characters in someone's historical research project, philosophical thought experiment, or sophisticated video game. The detection of simulation signatures presents intriguing theoretical possibilities. If our reality is simulated, there might be computational limits or shortcuts that would manifest as observable phenomena. For instance, if the simulation optimizes processing power by only calculating detailed physics when observers are present, we might detect subtle violations of physical laws in unobserved quantum systems. If the simulation uses discrete rather than continuous mathematics, we might find evidence of pixelation at the smallest scales of space and time. If the simulated universe has finite computational resources, we might observe limits to the complexity or resolution of physical processes under extreme conditions. Some physicists have proposed experimental tests for simulation signatures, such as searching for evidence that space-time is quantized rather than continuous, or looking for statistical patterns in cosmic ray data that might reflect the pseudorandom number generators used by the simulation's programmers. However, these tests face fundamental limitations because sufficiently sophisticated simulations might be indistinguishable from reality, and any apparent evidence for simulation could itself be simulated to maintain the illusion of authenticity. The moral and existential implications of the simulation hypothesis challenge our basic assumptions about meaning and purpose. If our lives are simulations, do our choices matter? Are our relationships genuine if the people we care about are programs rather than independent conscious beings? Should we behave differently if we suspect we might be simulated? Some argue that simulated experiences are just as valuable as non-simulated ones, that love and suffering and creativity retain their significance regardless of their computational substrate. Others worry that the simulation hypothesis could lead to nihilistic conclusions about the meaninglessness of simulated existence. The hypothesis also raises questions about the relationship between simulated beings and their simulators. Would advanced civilizations running ancestor simulations have moral obligations toward their simulated subjects? Should they intervene to prevent simulated suffering, or respect the autonomy of simulated beings? If we are simulations, might our creators be observing our behavior, evaluating our choices, or even interacting with us in ways we don't recognize? These questions become even more complex when we consider that the simulators themselves might be simulated, creating chains of moral responsibility, extending through multiple levels of reality. If every level of existence might be simulated by a higher level, then questions of ultimate meaning and moral authority become indefinitely deferred, leaving us in a universe where the foundations of ethics and purpose remain forever uncertain. The simulation hypothesis thus represents a unique form of parallel universe theory, one based on intelligence and computation rather than physics and cosmology. It suggests that the multiplicity of realities might arise not from quantum mechanics or cosmic inflation, but from the creative and investigative impulses of conscious beings who use their technological capabilities to explore alternative possibilities. In this view, parallel universes are not natural phenomena but artificial creations, digital worlds brought into being by minds seeking to understand their past, explore their future, or simply experience the vast space of possible realities that imagination and computation make available. If parallel universes exist, the implications cascade through every aspect of human existence, challenging our most fundamental assumptions about identity, morality, meaning, and the significance of individual choice in ways that are both liberating and profoundly unsettling. The prospect that every possible variation of your life might be playing out simultaneously across infinite realities forces us to confront deep questions about what makes you uniquely you, whether your decisions carry genuine weight, and how we should live when faced with the possibility that every story gets told somewhere, every path gets walked, every choice branches into actual existence, rather than simply fading into the realm of what might have been. Some people find the multiverse concept deeply liberating, drawing comfort from the idea that other versions of themselves have made different choices and experienced different outcomes. In quantum mechanical interpretations where reality splits with every decision, there would be branches where you took that job you declined, moved to that city you only dreamed about, said yes instead of no to opportunities that could have changed everything. The paths not taken in this reality would be fully realized in parallel worlds, ensuring that no possibility is truly lost, no potential permanently unfulfilled. This perspective can provide solace to those who struggle with regret or wonder about alternate lives, suggesting that every version of yourself that could exist actually does exist somewhere in the vast branching tree of parallel realities. Yet others find this same concept deeply unsettling or even paralyzing, questioning whether individual choices retain any significance if every possible decision occurs somewhere across the multiverse. If there are infinite versions of you making every conceivable choice, does it matter which particular path you follow in this reality? When you decide between alternatives, are you genuinely choosing your future, or are you simply discovering which branch of an already determined tree you happen to inhabit? The multiverse could transform decision-making from an active process of shaping your destiny into a passive recognition of which predetermined path you're following through the landscape of infinite possibility. These questions strike at the heart of philosophical debates about free will, moral responsibility, and personal identity that have puzzled thinkers for millennia. If every possible action occurs somewhere in the multiverse, Can we be held responsible for the particular choices we make in our branch of reality? Does praise or blame make sense when alternate versions of the same person are simultaneously making opposite decisions? The traditional notion of moral accountability seems to assume that individuals have genuine agency in determining their actions, but multiverse theories suggest that all possible actions occur simultaneously across different realities, potentially undermining the foundations of ethical reasoning. Philosophers have debated whether multiverse theories actually undermine ethics, or whether moral responsibility can survive in a world of parallel realities. Some argue that moral significance emerges from the local context of each branch, that the suffering and joy experienced in our particular reality matters regardless of what happens in alternate worlds. From this perspective, the fact that other versions of you might be making different choices doesn't diminish the importance of the choices you make here and now, because those choices determine the specific path that this version of you will follow through the branching structure of reality. Others contend that the multiverse changes the entire framework within which we think about ethics and meaning. If every tragedy occurs infinite times across parallel worlds, if every act of kindness and cruelty is repeated endlessly with infinite variation, then perhaps the traditional focus on individual actions and their consequences needs to be replaced by a broader perspective that considers the overall patterns and tendencies across the ensemble of all realities. This might lead to new forms of ethical reasoning based on statistical arguments about the distribution of outcomes across the multiverse, rather than the specific consequences of particular actions in individual worlds. The implications extend beyond ethics into the realm of personal identity and the continuity of the self. If there are countless versions of you across parallel realities, which one represents the real you? Are you a unique individual experiencing one particular timeline, or are you a pattern that exists in multiple instantiations across different branches of reality? When you make a decision that splits the quantum multiverse, do you continue as one continuous self, or do you divide into multiple selves that each believe themselves to be the continuation of your original identity? These questions about identity become particularly acute when we consider the gradual divergence of parallel selves over time. Initially, alternate versions of you might differ only in minor quantum-level events that have no noticeable effect on your conscious experience. But over months and years, these small differences could compound into major divergences in life history, personality development, and even fundamental values and beliefs. The version of you in a parallel world might eventually become so different that you would barely recognize them as yourself, yet they would have evolved gradually from the same starting point through an unbroken chain of causal connections. The multiverse also raises existential questions about the meaning and purpose of individual existence. If there are infinite variations of every possible story, if every conceivable narrative finds expression somewhere across parallel realities, what distinguishes your particular experience as special or significant? Traditional sources of meaning often depend on the uniqueness of individual lives, the irreplaceable nature of personal relationships, the historical importance of specific events and achievements. But in a multiverse where everything happens infinitely often, uniqueness becomes problematic and historical significance becomes relative to particular branches of reality. Some find meaning in the very vastness of the multiverse, drawing inspiration from the idea that existence encompasses such extraordinary richness and diversity that consciousness can explore every possible form of experience across infinite realities. From this perspective, you are not just one isolated individual, but part of a cosmic pattern of consciousness that instantiates itself across countless worlds, experiencing every possible variation of awareness, creativity, love, and discovery. Your particular version of consciousness contributes to this vast symphony of experience, adding your unique perspective to the infinite chorus of parallel selves exploring the space of possible realities. Others struggle with what they see as the existential weightlessness of multiverse existence, the sense that individual lives lose their gravity and significance when embedded in infinite repetition. If every moment of joy and sorrow occurs countless times across parallel worlds, if every achievement and failure is replicated endlessly with infinite variation, then the traditional sources of life's meaning, the sense that our choices and experiences matter because they are unique and irreplaceable, become difficult to maintain. These philosophical challenges don't have easy answers, and different people respond to multiverse implications in vastly different ways, depending on their temperament, values, and existing beliefs about meaning and morality. Some embrace the cosmic perspective that emerges from considering our place within infinite realities, while others prefer to focus on the immediate reality of their experienced world, regardless of what might be happening in parallel universes. The multiverse forces us to confront questions that may ultimately be unanswerable, but that illuminate the deep assumptions underlying our sense of self, purpose, and ethical obligation. Perhaps the most profound implication is that multiverse theories, if true, transform the entire context within which human life unfolds, changing not the facts of immediate experience, but the cosmic framework that gives those facts their meaning. We remain biological beings with the same needs, desires, relationships, and challenges, but we exist within a reality so vast and strange that traditional concepts of identity, choice, and significance require fundamental re-examination. Whether this transformation ultimately enriches or impoverishes human existence remains an open question that each person must answer for themselves as they navigate the profound implications of living in what might be just one thread in an infinite cosmic tapestry. And so we reach the end of our journey through possible realities, though if the many worlds interpretation is correct, other versions of you are still listening in parallel branches, each following slightly different paths through this cosmic maze of ideas and implications. We've wandered from quantum mechanics to cosmic inflation, from mathematical universes to digital simulations, exploring theories so vast and strange that they challenge our most basic assumptions about existence itself. We've encountered the measurement problem that drives some physicists to accept infinite parallel worlds, the fine-tuning puzzle that makes cosmic multiverses seem necessary, and the unreasonable effectiveness of mathematics that suggests abstract structures might be the fundamental substance of all realities. Throughout this exploration, we've grappled with a central question that threads through all multiverse theories. What does it mean for something to exist if it cannot be observed, measured, or verified through experiment? This question strikes at the heart of scientific methodology and reveals deep tensions between mathematical elegance and empirical grounding that continue to divide the physics community. Some of our most successful theories naturally predict the existence of parallel universes, but these predictions concern realities that may remain forever beyond the reach of direct observation, trapped by the very quantum processes, cosmic horizons, or mathematical boundaries that create them. The honest answer to whether parallel universes really exist is that we simply don't know, and this uncertainty itself tells us something profound about the limits of human knowledge and the nature of scientific inquiry. We have sophisticated mathematical frameworks that elegantly solve genuine puzzles in physics while predicting vast multiverses of unobservable realities. We have tentative observational hints that might be consistent with multiverse models, but could equally well reflect more mundane phenomena we don't yet fully understand. We have philosophical arguments about fine-tuning and anthropic selection that seem to require multiple universes, but rely on statistical reasoning about infinite quantities that may not be meaningful. What we're left with is a peculiar situation where brilliant minds have constructed detailed theoretical descriptions of infinite realities while remaining unable to definitively establish whether those realities exist beyond the abstract realm of mathematical possibility. The theories are rigorous, the mathematics is sound, the logic is internally consistent, but the connection to physical truth remains tantalizingly ambiguous. We find ourselves in the strange position of having maps of territories we may never be able to visit, descriptions of worlds we cannot observe, equations that predict realities we cannot verify. This uncertainty doesn't diminish the value of multiverse theories as intellectual achievements or tools for understanding the conceptual foundations of physics. Whether or not parallel universes actually exist, the theories that predict them have advanced our understanding of quantum mechanics, cosmology, and the relationship between mathematics and physics. They've forced us to confront deep questions about the nature of existence, consciousness, and scientific explanation that might otherwise remain unexamined. They've revealed hidden assumptions in our thinking about reality and opened new avenues for theoretical exploration. Perhaps that's the most appropriate way to think about parallel universes, not as settled facts about the structure of reality, but as profound possibilities that expand our conception of what existence might encompass. They remind us that the universe we observe directly represents only a tiny fraction of what might exist, that reality could be far stranger and more wonderful than our everyday experience suggests. Even if parallel universes remain forever unobservable, they serve as powerful tools for thinking about the deepest mysteries of existence and our place within whatever vast structure of reality actually underlies our observable cosmos. The implications for how we understand ourselves and our cosmic situation remain profound, regardless of whether multiverse theories prove correct. They challenge us to think beyond the boundaries of direct experience, to consider possibilities that stretch the imagination, to grapple with questions about identity and meaning that have no easy answers. Whether we exist in one universe among infinitely many, or in the only universe there is, we remain conscious beings capable of contemplating these extraordinary possibilities, capable of using mathematics and reason to explore ideas that extend far beyond the reach of our senses. There's something deeply moving about this human capacity to conceive of and seriously investigate the possibility of infinite parallel realities, to follow mathematical logic wherever it leads, even when it takes us to conclusions that sound like science fiction. It speaks to the remarkable scope of conscious intelligence, our ability to transcend the immediate circumstances of our existence and explore abstract possibilities that may encompass everything that could ever be or ever have been. As you settle into sleep tonight, wherever and whenever you are in this reality, or perhaps infinitely many others, consider that the very fact we can ask these questions, can contemplate the possibility of parallel worlds, can use reason and mathematics to explore the deepest mysteries of existence, represents something extraordinary in the cosmic story. Whether we're alone in our universe or accompanied by infinite variations of ourselves across parallel realities, we remain remarkable manifestations of the universe's capacity for self-awareness and wonder. Sleep well, fellow traveler, knowing that whether parallel universes exist or not, the mystery of consciousness contemplating its own cosmic context remains one of the most profound and beautiful phenomena in all of existence. In this universe, or infinite others, the capacity for awareness to arise from matter and energy, to ask questions about its own nature and origins, to dream of possibilities beyond direct experience, continues to unfold in ways that fill the cosmos with meaning, wonder, and the endless possibility of understanding. Sweet dreams, wherever and however many times you might be having them across the vast, strange, and possibly infinite landscape of all that might be real.